Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, it's my pleasure to welcome Amin Ansari here from the University of Illinois. Amin did his PhD at the University of Michigan and has been on a postdoc position at Illinois. He comes very highly recommended and has a great stream of accomplishments in architecture, and so I'm really looking forward to hearing your job talk, which you've told me has been practiced many times, so it'll be perfectly smooth.
All right, hopefully. It puts a little bit of pressure on me. Okay, good morning, everyone, and welcome to this talk. Thank you so much for the introduction, Doug. I went to University of Illinois after winning National Science Foundation Computing Innovation Fellow and started working with Josep Torellas after finishing my PhD. And today I'm going to give an overview of what I've done the last few years on a topic that I think is central to computer architecture as we get to the end of Moore's Law. The title of this talk is Optimizing Power Efficiency and Reliability in Extreme Scale Computing. Here I'm going to start by looking at the significance of power and energy efficiency. As you know, improving energy efficiency has many implications, and here I'm going to start by looking at a few of these implications. The first thing is there are many devices that are battery operated, and they are becoming more and more popular, such as PDAs, laptops, and medical devices. And basically enhancing the energy efficiency can prolong the battery life of these devices. For more throughput-oriented systems, such as data centers, basically cost is a more pressing issue, and this cost includes the cost of cooling, electricity, thermal packaging. And enhancing the energy efficiency of in such a domain can save millions of dollars for a typical data center per year. At the other end, we have the device lifetime. High power consumption leads to hot spots on the chip, and since wear-out failures are highly dependent on the chip's temperature, enhancing the power efficiency can prolong the lifetime of all the computing devices. And basically, if we focus on power and energy efficiency, we can enhance all these different aspects at the same time. Now we are looking at the trade-off between energy and reliability. I have a plot that shows the energy per operation on the y-axis, and we have the supply voltage on the x-axis. And this is for a typical CMOS process. We start with the dynamic energy, and as you can see, while increasing the supply voltage, we have this quadratic increase in the energy consumption. The next is the leakage energy, and as you can see, for the low voltages, we have this exponential increase in the leakage. If we put these two together, we're going to get the green line that shows the total energy of the operation, and there is an optimal point that is at the very low voltages. Now, if we consider the cost of reliability, this is going to change a little. Since at ultra-low voltages we will have an excessive amount of voltage noise, you need to deal with the timing failures that are arising in that region and repairing these faults.
What are you defining as reliability?
Reliability meaning that you can accomplish the operation that you're supposed to do.
So if I went out, though, the reliability is going to go way up as well. You'll punch through oxides or whatever. So what kind of supply voltage are you talking about here?
Yeah, this is mostly for up to like 1 volt, for example, to 0.2 volt. That is a reasonable voltage range. Yeah, you're right. If you go to like 5 volt, probably you have your wear-out failures will be so like dominant that you need to have some other reliability mechanism at that point. That's true.
So the reliability mechanism here is just bit flips due to noise?
Mostly timing faults, that meaning that the circuit cannot make the timing constraint that you put on it, and it can cause a bit flip in the output that you have. Yeah. Go ahead.
to understand the blue line, I understand that as you design the circuit for that supply voltage. Because clearly, if you reduce the supply voltage of the same circuit, you wouldn't lose more energy.
That's true.
So basically, as you reduce supply voltage, you thin out the oxide.
That's true. Yeah, that's true. Exactly.
So I don't agree with your answer. So if I'm having timing violations, I can just slow down my clock. I mean, you're slow. You know, when you're moving your voltage, you're slowing your clock anyway.
This is assuming the alpha power model for clock scaling. That basically you're not gonna slow down your circuit by like a factor of like 1000x in order to allow it to operate. It's assuming that like a semi-linear relation between the voltage and frequency, how the circuit will act.
Sure.
Yeah, you're right, absolutely. If you are willing to reduce the clock frequency by like 1000x, basically you can let the circuit work.
I care about correct results.
Yeah.
Maybe is where you're going, so
Exactly.
hold off.
I'm assuming also that the reliability cost is for unreliable operation that gets detected early enough not to cause mischief. Because if unreliable computation activates an airbag on me, that may be expensive in the next lawsuit.
That's true.
Not to mention ICBMs.
Okay, so if we put this reliability cost, we add this reliability cost to the green curve that we had, we're going to have this red curve here that basically there is a substantial shift in the minimum in the optimal operational voltage of the operation toward the right side, but still one can decide to operate at the reasonably lower voltages that at that point you don't need to go ahead.
The units that let you add those?
Sorry?
Thank you. Exactly my question.
What are the units that let you add energy and reliability?
What's the unit?
What is the units of reliability cost?
It's basically in terms of this is a schematic plot showing the trend, so there is no exact number on it, but in the cost is basically the cost of detecting the fault, recovering or repeating the operation, or rollback, basically any mechanism that allow you to repeat the calculation and get the correct result.
So the units are energy.
Yeah, definitely. That's
That's the answer to the question. So you're assuming that there's an energy cost to maintain reliability,
Exactly.
and you can do it with redundant computation, but
Yeah.
you're doing it with a checkpoint-based architecture.
something like that.
Well, yes or no?
Yeah,
I see.
I guess yes.
Yeah. Okay.
Thank you, Greg.
So we either can operate at a region like, I don't know, 1 volt that you wouldn't observe any failures due to the process variation, or you can choose to go for these lower voltages and try to operate at the optimal voltage value and basically save some energy at that point. And you need to have this aggressive energy efficient techniques that can trade off reliability for energy efficiency and still can tolerate some of the errors that are happening in this region. And in the rest of this talk, I will look at the ways that we can achieve this low voltage operation by efficiently tolerating some of the errors that are happening in this region.
I'll go ahead, Scott.
Are you making a distinction between errors that occur versus errors that have an impact or not?
These are the by errors or faults here, we mean that faults that you can detect and you need a mechanism to correct it.
He's assuming that no errors actually manifest in architectural state eventually.
Yeah, you need to correct it.
But if I, for example, had a bit flip in an uninitialized portion of the cache,
That's true.
that's not an error under your definition, or it is an error?
You're talking about architectural masking and like micro-architectural masking and different type of phenomenons in that category. Here, by failure, we mean that something that can potentially corrupt the architectural state of the program.
Okay.
I have one more question. Notably absent when you shifted from power to energy is any discussion of performance.
We will discuss performance later, but at this point, the thing that we are trying to do is basically assuming linear scaling of the performance with voltage, how this circuit will react, basically.
Yeah.
But that's a very good could question that energy and power, basically there's a notion of performance there as well, and you need to look at it.
I guess
That's
my
true.
better point was that you're presupposing here that the optimal energy point is your desired operating point, and I'm not sure that it is.
We are targeting like near threshold domain, and for those type of systems, basically the main criteria is energy, I think, or at least we are assuming here is like energy is a very big factor. Like if you care about the battery life and like cost of calculation, like electricity bill, like some of those kind of map to the energy. But you're right.
Threshold device, people use it because they care only about energy, not about performance, which is why no one uses it.
Yeah, I guess as I go through the talk and will present some of the schemes, you will see there is a variation between the schemes that I present. Some of them more care about the, like getting a constant throughput out of the system. Some of them are willing to sacrifice some of the performance that you can get.
Okay.
But this is the general trend. I wanted just to discuss that how the behavior of the system is as we go for the lower supply voltages. So now, looking at this low voltage operation, VDD is known to be the best lever for energy efficiency that can gain a very big reduction in dynamic power and static power. And as I mentioned, we want to have this near threshold voltage operation. That means we want to reduce the supply voltage to a value that is a bit higher than the threshold voltage, which maps to around 500 millivolt for the current technologies. And the main advantage that we'll get is that we can get a very big reduction in the power and energy, but the main drawback is the speed of this, the chip can go substantially lower, like a 10x is something that's very typical. And another thing is that we will have a substantial increase in the gate delay variation. That's a big obstacle in the way of this low voltage operation.
So sorry to keep hassling you.
No, go ahead. I
you're-
actually enjoy having this conversation.
Okay, so you make a bold statement that VDD reduction is the best lever for energy efficiency.
I have discussed this with many people, and actually, this isn't. I wouldn't be comfortable saying best. I would prefer. That's true. I would say one of the best.
Okay,
It's definitely one of the best. I'm not sure whether it is the best one or not.
well, I would argue that specialization gives you a much bigger
Better,
gain in energy
yeah.
efficiency than VDD does.
That's true, but for general purpose computation, like the circuit techniques you can do are very limited. You're right. If you have like a completely application-specific processor, it probably gains like several orders of magnitude better energy efficiency. That's true. I agree.
To make sure you understand, so you save 4x on energy per computation, you do it 10 times slower, and you save 4x on energy.
Yeah.
So the 40x is good marketeering, but not quite as
Still
good
good
as
enough. All right, that's good. Thanks.
You do near threshold and not sub-threshold because...
No, we are not going to discuss sub-threshold.
Because?
Because in general, I guess the sub-threshold circuits, you expect a very, very large raise in the fault rate. Very, very large. And you need a completely new techniques at the circuit level to deal with it. Generally, the architecture techniques can deal with failure rates that are reasonably high, but not super high. Like not one every out of 10 instructions will go wrong, something is going to go wrong. For sub-threshold, you generally need to deal with failures at a very, very aggressive manner. And also the performance that you get out of the circuit is very low in general. Mostly sub-threshold applications that I've seen are for like medical devices that like you put a chip for like a pacemaker in the heart, that performance is pretty much not a relevant issue. So in this near threshold, we're still hoping to get a decent performance out of the system. Yeah. All right. So as I mentioned in the last bullet, variation is one of the obstacles that we have here. And since it's an important issue, I'm going to explain a little bit more on what is parameter variation and how it's going to affect the chip. Basically, it's defined as the deviation of device parameters from their nominal values, and two of these parameters are threshold voltage and effective channel length, which are more important for the modeling purposes. And here I have two plots. The one on the left-hand side shows the static power versus threshold voltage. And when you have a nominal chip, basically there's a nominal threshold voltage, and that maps to a certain static power. As you add to the parametric variation, the thing that happens is that you will have some devices that have lower VTH, and some of them have a higher VTH. And the ones that have a lower VTH, since this curve is exponential when you are going for the lower VTH values, the ones that are at the end, at the lower end of this curve, they will have an exponentially higher leakage power. So the thing that happens is that the net effect of all the devices that you have on a chip will be a substantial increase in the leakage power of the system. And on the right-hand side,
Per device variation, not per chip.
this is the variation. This is static power of a particular device, of one device. But inside the chip, when you add to the parametric variation, some of the devices will end up having a lower VTH, some of them higher VTH. And the ones that have lower VTH, the static power is much higher. Therefore, the net effect that you will get across the chip is basically a substantial increase in the static power. On the right-hand side, I have a plot that shows the distribution of path delays for a pipeline stage. And on the x-axis, we have the delay, and since the path that has the worst timing characteristic will determine the clock frequency, that tau nom, for example, is the delay, is the corresponding frequency of the chip in this case. As you add to the parametric variation, this plot becomes more flat, and the tail will shift to the right side, and some of the paths will have a much worse timing characteristic. Therefore, the clock frequency of the chip needs to be reduced substantially. As a result, both power consumption and the delay become pressing issues while we are targeting this low voltage operation. All right, here I have the roadmap of this talk. Our objective is to enable low voltage operation of high performance microprocessors with comprehensive low cost solutions. And I have worked on...
Performance processors in near threshold regimes?
Actually, that's the objective of this talk. Yeah.
Okay.
I will try.
All right.
You can
Great.
See how it goes. So I work on several different areas, but given the limited time that we have in the rest of this talk, I will present 3 solutions that I've proposed to tackle this reliability and energy efficiency in some of the main components of a high performance microprocessor. We're going to start by looking at network on chip. I'll present Tangle. That's the work under submission. It's a collaborative research with Intel Labs on their DARPA and DOE grants. And the objective is to dynamically do the voltage adaptation based on the errors that we observe in the network. After that, we are going to look at cache hierarchy. I'm going to present Archipelago, which is a work that I published in HPCA 2011. It's a highly flexible cache architecture that tolerates the SRAM failures at near threshold domain. And at the end, I will present Necromancer, which is a solution for processor pipeline. It's published in ISCA 2010, and the extended version was published in IEEE Micro 2010. And the objective here is to protect the processor pipeline with energy-efficient solutions. And at the end of the talk, I will present some of the potential future research directions and also give a brief overview of my other research accomplishments. So we're going to start with network on chip. What is the impact of variation on NOC? Network on chip is especially vulnerable to variation. This is because this routers and links connecting very distant parts of the chip, and due to the systematic variation, they will exhibit very different speed and power characteristics across the chip. Therefore, you need conservative voltage guard bands to tolerate the process variation. And it has shown in the prior work that network on chip can consume up to 40% of the chip power. Therefore, since the power is strongly proportional to the supply voltage, there is a great opportunity here to save some energy by reducing some of these guard bands that has been added for tolerating process variation. Here to demonstrate the impact of variation on the routers, I have a plot that shows the probability of error versus supply voltage for a 64 router 2D mesh with 1 voltage regulator per router. And in this plot, as you can see, there are 64 curves, and each of these curves show the failure rate of a single stage of a single router. And
Describe what you mean by having a voltage regulator per router. I thought this was a network on chip.
yeah, we have one regulator per router inside the chip. Yeah, it's a mesh network, for example, that you have many routers.
So, how much area does 64 voltage regulators take?
That's a very interesting question. I have multiple answers to that. One of them is that in order to do the limited study of how much can we potentially get, we did a study with 64 routers per chip. We can change the scheme so that you can combine some of the routers and put like 4 or 8 of them in the same voltage regulator. Sure. Another way to implement it, that there are LDOs that there are like low drop-off voltage regulators, and you can implement this thing in a hierarchical fashion. Put like each, I don't know, 4x4 sub mesh inside one of the voltage regulators and use LDOs close to each of these things, since the variation in the voltage of each of them is very small. Basically, the thing that LDO is doing is that it can vary the voltage by a very small amount, like 100 millivolts, for example. And given the systematic variation, the ones that are close to each other showed kind of similar behavior. So you can set the voltage of the whole, like a sub-mesh, like a 16 router sub-mesh, with a regulator, with the on-chip voltage regulator, and then tune each of them using an LDO, which is very, very high efficiency and low cost.
Okay.
That was a great question. So, as you can see, as we go from high voltages to the lower voltages, the thing that happens is that the failure rate is extremely low. And as we go higher, we basically go to this steep curve, and gradually we get to a failure rate that is almost 1, and which meaning that all the time you're going to fail. You're going to have failure in your computation. And this curve is very steep. That shows process variation has a major impact on the routers. And one thing that I want you guys to look at is that at the error rate around 10 to the minus 18, which is a relatively low error rate that allows fault-free operation for a long time, you can see there is a very large variation of the voltages across the chip from almost 530 millivolt all the way up to 750 millivolt. And this means that if you have a scheme that can adapt the voltage of each router based on what is the minimum VDD at which it can comfortably operate, you can save a substantial amount of energy in the network. Our estimation shows 30 to 40% can be easily achieved.
I think this chart is showing systematic process variation for across the chip was the setup, but you're now arguing, or is that incorrect?
Go on.
Okay. But now you're arguing that you want to have per router or much more local control of these. I mean, this chart to me says we ought to bin our parts, which we do already.
But no, the network is in one chip, so all the routers are basically in one chip. How can you bin it?
That's how I read it.
But he earlier was talking about systematic process variation.
Yes.
What hits his network on a chip.
Inside one chip. So if you manufacture one chip, inside of that chip, if you measure the voltage at which each of these routers can have this error rate, that's what you're going to end up having. Like for some.
Each of these curves is a single router inside the chip.
Exactly.
And that entire router is assumed to be at some process value, but different routers have different variations of the process.
We actually use Variant, which is a tool that's developed in University of Illinois that does process variation modeling at a very detailed manner. And basically, we did the synthesis and we got the net list of different routers and basically calculated the logic effort of each of those paths and kind of like feed them to Variant to get this result here. So it includes the impact of variation on each of these single routers.
And all the curves are identically shaped under that?
Yeah, all of them pretty much have the same shape, meaning that as you decrease the voltage, the failure rate moves in a similar manner, like increase in a similar manner on all of them. So what's the main idea behind our approach? Basically, we are trying to achieve high energy efficiency by removing the VDD's margin that is added for variation and wear out, while keeping the frequency constant. So here's the kind of an answer to one of the questions that Doug asked, that what's going to happen to the frequency and the performance. Here our objective is to keep the frequency of the chip constant and try to remove any margin that is added for variation and wear out purposes. And we reduce, the way that we are going to do this is that we are trying to reduce the VDD of each of the router to the minimum level that it can comfortably tolerate. And we start by having a high voltage for each of these routers. As you saw in this plot, something around 800 is a safe voltage, and all of them can operate correctly and allows a fault-free operation. And we periodically decrease the VDD, and we monitor the errors that are happening inside the system, and if needed, we're going to increase the voltages. And we rely on some inexpensive error detection. Since we want to have only a few bits added to each packet, we're going to use CRC, and since we want to do the error checking as infrequent as possible, we're going to do end-to-end. Basically, once we do the encoding at the source node and we do the error detection at the destination node.
So this is more of a protocol question, because this is something that we've been wrestling with. Scott, I'm sure, has a lot of thoughts on this too. So if you're not going to run the network at a guaranteed reliable state, then you're going to start flipping bits in your packets.
That's true.
And you're going to put your router in all sorts of very, very scary conditions.
That's true.
Right? So you can route stuff randomly, you can change the destination node. How do you guarantee that you're not going to deadlock your network? How do you provide any protocol guarantees on top of that if you're not going to drain packets that have been corrupted, at each node?
That's a great question. I will describe the scheme, and I will try to answer your question there. That's a very, very great question. Okay, as a result, the thing that Tangle is trying to do is dynamically changing the supply voltage of each router based on the errors that observe inside the network, and that this allows us to adapt to the workload phases, temperature, and also the wear out. So here I'm going to describe how we handle the errors inside Tangle. We continuously monitor the errors, and when an error occurs, the destination node drops the fleet and waits for a retransmission from the source node. At the source node, we have a watchdog timer for each of the fleets, and when the watchdog timer reaches a certain value, the source node sends a signal to our reliability management unit and asks for a VDD increase. Given the deterministic routing, the reliability management unit knows what subset of routers it needs to increase the voltage on, because it's like a XY routing, and if there's a failure, it knows that what subset of routers this packet's supposed to go through, so it's going to increase the voltage on that path.
So how does the source node know that the flip was dropped?
Source node has a watchdog timer that if it doesn't get if you don't get an ACK after a certain amount of time, you know that something was wrong, and then you tell your reliability management unit that something was wrong. Do something for me. Here is me, and here's what is the destination that this packet's supposed to go through. Actually, I have examples of this thing in the next slide.
I don't need an example. I understand the policy. You're assuming that the source node is going to buffer everything until it receives an ACK. And what if the ACK gets corrupted and gets sent somewhere else?
That's a very good question. The same thing happens. Basically, if the ACKs get corrupted, the source node still didn't get the ACK, so it's going to have a timeout. Yeah. So it knows that the routers that this ACK is supposed to go through has some problem as well.
But how does it know whether or not to? So now it's going to retransmit something that's already been correctly received.
No, but you do a voltage increase and then retransmit.
Yeah.
So I think what Doug is getting at now is that the destination got the message.
Yeah.
And so it believes it's moving forward, but it's going to later on get another copy of that message because its ACK got dropped.
That is true. I guess that at the destination node, we can either use the reliability management unit to tell the destination node that, okay, this is a duplicate message, because that one knows that what message is going to get to the destination node as a duplicate, because that's the thing that's the request that it got from the source node.
Wait, where is the reliability management unit is somewhere on the network, right?
It's a distributed unit, yeah, inside the network. Basically, we build it in a hierarchical fashion. All the source nodes are connected to that unit.
So you're going to get another copy of the message, and so whenever you get a message, you have to talk to the reliability management unit to see if you've already received this message.
No, reliability management unit can send you like an interrupt that says that, okay, if, like, because first it increases the voltage on a particular path, and then the packets will go through. So it knows that which node will eventually get a duplicate.
I don't care about the voltage increase, because I could just assume that it does it wrong the first time and does it right the second time. I mean,
That's pretty much what's happened.
Yeah, so, because, other things can corrupt network packets, so you can't assume that it's always correct. You just increase the voltage and your probability of an error is lower.
Yeah.
So whenever I receive, so if I'm a destination, whenever I receive a message, I have no idea whether I've already received this message or not, because this could be a retransmission.
Yeah, but the reliability management unit knows that you're going to receive this packet again, right?
How?
Because originally, when this packet got transferred, and then there was a timeout at the source node knew that this packet needs to be retransferred again. So when it sends that packet to the reliability management unit and says that a problem happened in this packet, the reliability management unit knows that this is going to be retransmitted. And it already knows the destination node for that.
So which is, there is some network between the reliability management units at each source and destination
All the
that's communicating things. And is that also just as likely to be buggy, or do you have something to deal with?
No, that operates at the higher voltage always. Yeah. That network is always operating at maximum voltage, or 800 millivolts, so that you don't observe errors in that.
So I receive a packet, the CRC checks out. I receive another packet, and when I receive that packet, how does the network, the reliability management unit, tell me that that's a, I mean, I could set a bit in the header that said this was a retransmit. But I mean.
So do you want an answer or his answer?
There can be different.
I'm not sure.
Yeah, one of the ones that I was proposing was that reliability management unit basically knows that this packet is definitely going to get retransmitted. So it can tell the destination node that there will be a duplicate of this message, so you can just send an ACK and drop it. Or, as you said, you can have a bit.
Okay, so I guess what I'm uncomfortable with, I don't care about the reliability management unit, because I can also set a bit in the header that said this is a retransmit.
Yeah, that's true.
I can adjust the state. But when I receive this duplicate packet, what do I do with it?
Just drop it. And send an ACK to the source.
But how do I know if I've already consumed it or not?
If the CRC check
all right, here's a scenario. I'm sorry to harp on this, but this I'm not sure this works. So I receive packet A.
Yeah.
And what's that?
I think he's okay. So
okay.
Keep rolling if you want him to get
all right.
you
I receive packet A. I'm going to consume it. I'm not going to buffer it, waiting for an ACK on my ACK.
All right.
Yes.
Right?
That's right.
I consume it.
Yeah.
Now, and I send an ACK back. The ACK gets dropped or routed somewhere else. Somebody else receives an ACK. God knows what happens
Let's
next.
just make it disappear.
Yeah, make it disappear. All right. And actually, the CRC will catch that.
Yeah.
Right. So now I send packet B, which is the same as packet A, and I have some state that says that this is a retransmit. And now I receive packet B. Do I consume packet B?
No, you're gonna just drop it.
But what if packet A was dropped and I got packet B? Like if packet A was sent to the wrong place, and it timed out. Then it sends packet B, and I get packet B, and it says, okay, now great, I can.
No, but at the destination, you know that, for example, you see that you have a number for like a packet number or something, and you know that whether you consumed it or not, right? And when you get a duplicate, you know whether this number matches that one or not.
So you're saying that I need to keep a log. I need to come up with some unique ID for every packet I consume.
In an instruction,
And keep a log of all of those packets, and then do a cam against them to make sure that the packet that arrived isn't sitting in those?
Yeah, not for, like the log wouldn't be that long because that would be the latency of basically doing this retransmission and changing the voltage.
Just a network, how can you bound the latency?
Congestion is actually like a chapter in the paper, like how we deal with the congestion.
Well, no, not how do you deal with congestion, but how do you see where I'm going? Like,
I know where you're going and I know how to solve it, but I don't know whether you want me to take you there.
Yes.
Okay, so all you need in the destination is a piece of information for each source which says what is the packet ID that I have successfully gotten. And I'm going to make a rule that says once a packet is
You're guaranteeing in order delivery.
We're assuming in order delivery.
Okay, all right.
And so what you do is when a packet arrives, if it is the next one, you increment that value, you consume it, you send the ACK back.
Yeah, okay.
And then if it is either too large or too small compared to that, if it's too large, you drop it. If it's too small, you drop it and ACK it.
Right.
And I think you're fine.
Is that what you do?
Sounds a very interesting answer. We assume that a mechanism can be used to handle this.
So you haven't thought about this problem?
No.
Okay.
Rather than put the watchdog timer in the router and having an ultra-reliable network to say I got a bad network, can't you put the watchdog timer in the reliability unit and then you send messages that things are okay, and if they don't arrive, it starts jacking up the voltage, or there will be too many messages?
That's an interesting question. So you're saying that put the watchdog timers in the reliability management unit and send, basically acknowledge the things that are wrong, or
Acknowledge things that are right.
only the things that...
If a node says things are all right, don't do anything. If a node doesn't say anything, right, jack up the voltage. Then it can be as unreliable as the rest of it. You may have many more packets. I don't know that.
That's a different way of designing it. I think that makes sense. I don't know what are the trade-offs here, basically, if you put the watchdog timers in the reliability management unit. But my guess is that you need probably a lot more communication with the reliability management unit to realize what's going on with different packets. But that's an alternative. We were trying to keep the reliability management unit network very, very like low bandwidth, so you don't need so much communication on that one.
Are you going to talk about how you lower the voltage back down?
Yeah, I will talk a little about like what is the mechanism that we're using basically to change the voltage. So here I have an example of what's happening to the supply voltage of a particular router over time. And as I mentioned, we start with a relatively high voltage around 800 millivolt, and we gradually reduce the voltage at the beginning of each epoch. Basically, an epoch is a time period during which we first decrease the voltage and we monitor the network to see whether error is happening or not. If it's happening, we're going to increase the voltage. And we start with the relatively high voltage tuning step, and as we gradually get to the lower voltage values, we are going to reduce this tuning step. As you can see, for example, the first step is around like 60 millivolt or 70 millivolt, and gradually goes down to around 10 millivolt, which is kind of getting to the physical limitations of the voltage regulator. And for example, the thing that's happening in epoch 4 is when we are going down to around 600, 1020 millivolt, we're going to observe some errors in the network. We're going to raise the voltage and we continue the operation. We're going to decrease, and in the epoch 6, you will see that some other errors happening. And basically, the thing that's happening is that you gradually converge to a value that that router can comfortably operate at. You will see errors every now and then, but the overhead of fixing those errors are very, very marginal compared to the time window that we have here. So
if I am within a nanosecond of an epoch boundary and I get a request to, or whatever your smallest amount is, and I get a request to increase the voltage, you are in fact you get an error. You're going to increase it, decrease it almost immediately.
Immediately, yeah, true.
Okay.
Yeah.
So I still don't understand how you can guarantee that you don't deadlock, given that you're allowing corrupted messages to flow through the mesh. I'm sorry to keep harping on
Yeah,
network.
no. That's good. I actually kind of enjoy this conversation, so I don't mind it. You can.
So if I flip a bit and now it gets routed to the wrong place, and that's happening arbitrarily in the network, now I can end up with a circular dependence on resources and deadlock.
That's not going to happen. Let me show you the example of how it's working, and then we're going to discuss this particular example. Yeah. So here I have a very, very simple example. I think that you guys already have a very good vision of how it's working. Basically, it's a 4x4 mesh. The darker color means that router has been affected more by process variation and has a worse timing characteristic, and the lighter one means that it has a better timing characteristic. So we imagine that the ones that are lighter, we hope that they end up with the lower voltage values, and the ones that are darker with the higher voltage values. We set everything to 800 millivolt. We want to transfer a packet from core 1.1 to core 1.4. It goes through the, based on deterministic routing, goes through X and then goes through the Y. And it gets delivered without any errors. After a few epochs, the thing that's happening is that voltage of all the routers will go down to around 700 millivolt. And if we want to transfer the same packet, the thing that happens is that at router 1.4, we're going to have a fault. Then it's going to go to the next one, have a fault, and then deliver it. The thing that's happening is that at router 4.4, we're going to drop that packet, raise the voltage of all the routers on that particular path, and basically do a retransmission. And in the next epoch, basically, I have another example of another path that how the voltage changes happen in this path. Now going back to the question that Doug has, what's going to happen if you have deadlocks? So how can you have a deadlock? Basically, deadlock means that you have this problem starts at a particular node, right?
Are you assuming store and forward?
Yep. Yeah, let's assume that this problem starts at a particular node. Like let's think about this particular example that we want to transfer this packet over this path.
So,
at some point, this problem starts to happening, right?
You're doing store and forward at each router, so you're buffering the whole message before you send any data from that message on to the next router on an on-chip network?
Nah.
No.
No.
No, you're doing wormhole routing.
Yeah, definitely. It's wormhole routing.
Okay.
Sorry. Yeah, it's
So.
Okay. Yep.
Okay. So now, so to the point you're making, I have a problem at router 1,3, and it sends a message down, and I have a problem at some other router that sends a message up. And now the buffers are full, and they're both waiting for buffers to clear, but they're depending on each other. Okay.
So I think where Doug is heading was that the message, you want a message that where I actually corrupt the destination address, correct? Or
yeah.
not?
Yeah, I guess that's
Okay.
I guess the deadlock, one scenario that I can imagine is that the packet is going through the forwarding path, and at some point you will have a failure, and basically it gets to a loop here, for example, something like that.
Between two messages. Yeah.
Yeah. That's the scenario that you're describing, right?
Classic carry and cube deadlock.
Yeah, I agree. So the thing that's happening is that the voltage of this router was wrong, so it's doing something incorrectly, right?
No. So the voltage is only going to affect the error rate.
Yeah.
Okay. And if you up the voltage, you're going to change. You're going to improve the error rate. But I've already incurred the error, and now I've got a cyclic deadlock where the buffers are full and the messages can't make.
But we're going to flush the buffers.
Okay.
Yeah.
So.
But only once the incorrect CRC is detected at a destination, correct? Or are you going to flush on a
No. And the timeout at the source node.
Okay, so at the source node, you didn't get an ACK, which means you're going to up the power, and you're going to flush the entire network?
No, not the entire network. Just the ones in that path. Just the routers in that path.
But
Nope,
maybe,
that doesn't do it.
yeah, because I could have sent routers, I could have sent a message off that path. The message left the path.
Yeah. But either that message gets delivered to a destination or it doesn't. You say that it's not going to
All
get
right,
delivered.
here's the scenario.
Okay, go
All right, I'm routing from the top corner to the
Yeah.
bottom corner,
Yeah.
all right? And yes, this sounds unlikely, but we're running at large scale. So now I have an error where I'm now gonna route that message down this way.
Yeah, okay.
All right, so the bit gets flipped, and it's a long message, so it's gonna fill up the
I
buffers.
think you actually want to have the flip when it's coming down to go over, but keep
Well,
going.
well, actually, no, let's just say it goes down. You
Fine.
hear my example. And now I flip another bit, and now I try to send it from here to here, right? So I have two errors in the message, and now it's routing through and actually trying to route through itself.
Oh,
Okay.
sure.
I mean, you can construct a more likely example with two messages, right? And
Oh, I
that-
see.
That
And
message
you
is now,
have, and it's all off of
And it's all
his
off the path.
Yep, I see it.
But I kind of see what you're saying. The one answer that I have is that
buffers,
Yeah.
those nodes are completely wedged, but they're not sending or receiving. They're not going to time out. This guy times out because he doesn't get
Yeah,
an act.
that's true.
He flushes the buffers along that path, but the message is
So,
off that path, and you're never.
one is that the likelihood of a message getting into such a scenario that basically two faults are happening such that
You can do it with two messages with higher probability. I already said that. Don't.
All
Never argue that the likelihood of the deadlock
is
scenario
very
is
low.
low.
All right. I
Just
see.
remember, we're Microsoft. We run at
A
large
very large scale, so any corner case can happen. That's true.
Daily.
Okay, I guess that the only answer that I would have in that scenario is that you probably need to flush all the routers inside your network. That's the only way that's going to fix it at the beginning. Yeah.
I'll give you a handout. One of them is you can tell us why the message that was going down through from R23, R33 can't make that turn.
Yeah,
Or
because
you're going
of
to
the
tell me
XY.
about how Doug's stuck thing is eventually going to get flushed. And I think you might have an answer for either one of those.
Yeah, I think that one is that for because of the XY routing, that it cannot go through that particular path. It cannot go. Probably it doesn't. It's actually possible. I mean that if the fault is in a very very particular manner, that as Doug is saying that for a larger scale system it might happen.
So
It is possible. So I can see that happening.
A message
Yeah,
that will go from Y to X routing in your router?
is not Y to X routing. It's still X to Y routing. It comes here X, Y, and X, Y.
Save yourself now, I think, by saying the R23, R33 flowing message
Yeah.
cannot possibly go to R32. Is that true or is it not true?
This message going here.
Yeah.
It can if its destination gets flipped at R33.
I don't think it can. I believe you have a router that does all X's before Y's.
Yeah, but
So if you had a message that was moving on Y, you would never look at it and send it to X because that path doesn't
yeah, but
exist.
one scenario that I can
Yeah.
imagine that can happen is that this one says send a message to here, and basically you're going to send it here. Then this one says send it here, and basically in a loop you have these fault patterns that are like complementary. This one says okay. It's very very unlikely, but I can see that happening.
So then let me give you your second handout.
Or
Let's take Doug's scenario.
Alright.
Doug's scenario is you have a dog chasing its tail. One message, R23, 33, 32, 22,
yeah,
23.
exactly. That's what
Okay.
I was
Tell me
imagining.
what happens in that network when I go forward now. What messages are delivered in that region?
You mean the other messages that are
Other messages in your network are trying to be delivered in that region, are they?
They can be delivered. Because that message is gonna flow, so the other things are not gonna get stuck.
It's stuck.
Buffers are full. No flick can be transmitted.
But why the buffers are gonna be?
Because they're filled up with the message and they can't
Yeah.
be deallocated until the message makes forward progress, and the message can't. Because the head of the message is waiting for a buffer to be filled up, to be transmitted.
But what if all of them try to go through the same path?
I think that's
Where
what
Scott
we're
was
talking
going is that somebody's eventually going to try to transmit and they're going to time out.
Time out,
And then they're
and
going to
then
flush.
you're
They're
gonna-
going to flush that path.
Yeah.
You're gonna flush that path.
Right.
That's a very, very Interesting answer, yeah. I can imagine.
The deadlock stops stuff, in which case it stops stuff and your system will eventually recover. Or it doesn't stop stuff, and if it doesn't stop stuff, do I care?
Yeah.
Yeah.
That's true.
Okay.
Yep, thank you so much. All right, I guess that I described this particular example. So the thing that's happening is that eventually, basically, the system will converge to a state that that the voltage of all the routers are getting close to their optimal values. And the main reason for this is that the routers that have worse timing characteristic basically will end up being at the intersection of a larger number of paths. And those paths that are intersecting cause this router's voltage to go high up faster, in a faster rate compared to the other ones. Definitely for the very, very small networks, this might be not a correct statement, but we realize that, for example, for a 16 node mesh and upward, all the simulations will end up having a similar, will end up with a similar behavior. So in summary, we showed a dynamic route-oriented approach in order to save energy in network on chip. It adapts to temperature, workload phases, and wear out. And we try to achieve this in the presence of process variation by keeping the frequency unchanged, reducing the voltage of each router to the minimum value that they can operate at comfortably. And we efficiently tolerated some of the occasional errors that are happening in the network. Applying Tangle to a 64-node mesh, we were able to reduce the energy consumption of network on chip by around 28%. And this came with less than 5% overhead for a wide variety of benchmark suites.
So I want to talk about flushing the network now.
Yeah, right.
So when I flush a path,
Yeah.
I'm going to kill a bunch of messages that may be using routers along that may be sending along that path. That's right.
Yeah.
And so then they're going to knack, and so I'm eventually going to flush that path. So if I've got a highly congested network, why doesn't the flush create a cascade of flushes? That I end up with live lock.
It is possible. I can see that happening, that if you flush one path, I think it might make more sense to say that we're going to flush the whole network. These epochs are pretty long, so...
But even if you flush the whole network, you still have the same problem, in that you've killed a bunch of messages, and now those messages are going to time out, and they're, I mean...
No, but when you flush, you're going to reset the timer for each of them, basically. So you're not going to count as a...
So the first detected watchdog failure is going to be assumed to be the only problem you can detect at that point.
At that point.
You flush everybody, you penalize that path, and then you restart. And even if there were other problems in the system, you're going to detect them with some future message.
That's what it is.
Okay.
Yeah, I guess I didn't follow that. I still don't see, you know, I've killed a bunch of messages. I don't know if they've been delivered or not. So they're buffered at the source.
Yes.
And I have to wait to get a NAC.
Yes.
And I've killed a bunch of NACs, maybe of ACs, so I'm going to time out. And then when I time out, something's gone wrong in the network, and that timeout could be a deadlock, so I have to flush.
Yes.
So every time, based on your mechanism, every time you flush the network, you're going to kill some good messages if there's any traffic in the network, and then you're going to cause some timeouts, then you're going to flush again.
It was that last sentence where you're wrong.
Okay.
So I'm not exactly sure how he does it, but I believe the first timer goes off for the first message that is found to be a problem.
First timeout.
And he will then somehow wave a magic wand
and drain the network.
And drain the net. Well, just dump everything in the network, and then tell every timer that the messages you had in flight are not going to be considered to be buggy in and of themselves. They're going to be buggy because of the path I had. And so retransmit them and don't penalize, and reset their counters and don't penalize them for having been caught up in this. I think it's subtle, but I think it's doable.
Yeah.
I wouldn't want to write that code.
Assuming you have the mechanism.
And it's microcode.
Probably Verilog, even worse.
Yeah.
So while Doug's thinking,
No, I buy it. I'm just trying to think if there are corner cases. I'm just worried about the amount of source buffering that we have to do. And you have to buffer, and you have to have the detection of 64 nodes to see the message.
Actually, buffering at the source node is a very important thing. Actually, as I mentioned, we have some collaborators from Intel Lab, and buffering at the source node is the main thing that they mentioned about this work that might be a limiting factor. We tried to throw a study for the buffering, and one thing that we realized is that around buffering 64 flits at the source node is enough for a 64 node mesh network to have a relatively, to have a low performance overhead and make the system kind of working and not stuck a lot. But that's a big drawback, basically.
Okay.
Sorry. The source buffer you need is 64 flits.
Yeah, that was what we tried in some.
That's an empirical study.
Yeah, it's completely empirical.
Well, but how many messages is that?
It's we assume I guess six flits per message. Yeah.
Okay. And when you run out of buffering space,
You're gonna stall.
you just stall the
Yeah.
processor that's generating. Okay.
Yeah.
So you said that the voltage per router tends to get close to the optimal.
That's true.
How do you know that, or have quantified that? Or
That's
just
based on
roughly?
our static analysis, basically. We do a static analysis, as I showed in one of the earlier plots, that we have an idea of what should be the voltage of each of these routers going to end up to. And basically, at the end of the day, we'll do a comparison, and we see that the voltages that we get across the system are close to the ones that we got through the static analysis.
Okay.
Yeah.
So I want to do a quick back of the envelope. So
Go ahead.
how many cycles is it router to router, roughly?
I guess just the link itself or the whole message?
No. To get from
It's a
equivalent point
3-cycle route.
and the link is.
That's probably, we can assume it's 1 cycle.
But you're crossing clock domains, aren't you?
No, I said we keep the clock constant, that's the main objective.
Yeah, okay,
Voltage
all right.
domains.
Yeah.
So
You're
we already
you're
have
crossing voltage domains.
Yeah.
I mean,
Crossing
is that
voltage-
free?
You need voltage shifters, but it's not as bad as crossing the frequency domain.
I don't mean voltage. So, but is it free in terms of time?
It's not expensive, I guess.
All right. So let's say 4 cycles, which sounds a little optimistic to me, but 4 cycles, and you've got a 64 node network. So your average message transmit time will be.
But how many cycles is a
9.
flip?
12. 3 over 2 or something, 1.5 match. Like if it's 8, it's gonna be like 12.
Yeah. It'll be 8. Let's say 10. So it's 40 cycles for the first data packet to get through. And how many cycles does it take to get one flip through, based on your size?
To what?
A router?
The flit is how many cycles on the network. If your flit was, if
128
you
bits.
send 16 bits a cycle, and
128 bits, and how wide are your links?
It's 64.
All right, so it's two cycles. All right, so that's in the noise. And an average message is 6 flits. That's 12 cycles. So you're looking at, let's say 50 cycles to transmit a message on average across the network. And then it's 50 cycles to return back. That's 100 cycles round trip. How long does it take you to flush the network?
That's I actually don't have any.
Yeah. Okay. So because we've changed the flush policy.
Yeah.
So 100 cycles for message, if I've got 6 messages source buffered, that's 600 cycles.
I guess so.
Yeah. Well, I guess you could pipeline those, but what is your injection rate into the network? How often does a processor send?
I don't remember.
Okay.
I don't remember. We don't have a lot of different benchmarks. So my imagination, what I imagine is that there is different injection rates for different benchmarks.
Sure. So run Little's law and see.
Yeah, and see what.
Given the size of the window, you know, how and the number of messages in flight, how many you would need to buffer at the source before you started throttling. Because there's going to be a lot of stuff.
That also matter the locality in this, etc.
Yeah. Okay. Well, we can move on.
All right. Okay, so in the second part of the talk, I will discuss some of the works that we did on the cache. The main reason that I presented Tangle.
We only have about 10, 15 minutes left in your talk.
All right.
So we've grappled with this. Would you mind jumping ahead to the
Which one?
the Necromancer?
You like the
part of the talk?
Necromancer?
I'm just.
All right. All right, so since we have limited time, I guess I'll present the Necromancer, which is the work that is done in order to protect the processor pipeline. So assuming that I have presented the cache work as well, we've presented some works that can protect network on chip and cache. And in order to maintain an acceptable level of yield for the whole process, since the processor pipeline also consumes a substantial area of the chip, we want to have a mechanism that basically protects this part as well. However, this is more challenging since the processor pipeline is inherently more irregular. For example, in a network on chip, all the routers look the same. On the cache, pretty much everything is SRAM. So it's easier to basically have redundancy-based techniques to repair these structures. Here, we're trying to not rely on a redundancy-based approach and use an alternative to make the dead core do something useful and basically enhance the system throughput. In the next few slides, I'm going to describe how we're trying to exploit a functional dead core to achieve a better system throughput. So given that dead core contains a fault, we cannot trust that core to execute the program even for a short period of time. Then the question becomes that how can we exploit such a core? The approach that we're taking is to use that core in order to accelerate another core. We have this dead core that contains a hard fault in it, and we add a little core to the system that we call it animator core. Animator core is basically an older generation core running the same ISA with substantially less resources. And then we, sorry?
On chip or next?
Yeah, this is on chip. So animator core is running the main program, and we let the dead core also to run the same program. And we abstract the execution information on the dead core and extract some useful information from it that we call hints. And we send these hints to the animator core in order to enhance the performance of the animator core. Here, in order to see how much speed up we can potentially get, I have a study that shows the IPC of different alpha cores normalized to the most simple one. From left to right is a 2 issue in order, 4 issue in order, 2 issue out of order, and 6 issue out of order. And we want to use the first 3 as different
Six issues
out of order. It's EV6. So
it's 4 issue out of order. It can dispatch 6 instructions peak, but it will never sustain more than 4.
It never sustain one. In our experience, we actually use 6 issue. So basically, sorry if it's not EV6, EV6. Yeah, it's similar to EV6. We try to keep it 6 issue. Yeah, you're right. It might not dispatch 6. So the thing that's happening is that from left to right, basically the complexity of this core is increasing and it needs more resources. We're going to use the first 3 as different alternatives for our animator core and want to see that how much performance we can get by providing perfect hints. Here, perfect hints means that we're going to have perfect branch prediction, and we're going to have no L1 cache misses. So this yellow bar is showing that how much performance it's going to get. having that perfect hints for the animator core. As you can see, the thing that's interesting here is that if you can provide this correct hints for the animator core, the performance of a dual issue out of order can actually exceed the original performance of a 6 issue out of order. That means that there is a lot of opportunity for the acceleration. Obviously, providing perfect hints is not possible, but we are trying to do our best to get close to this chart, to this plot. So here is a little bit more detailed structure of Necromancer. On the left-hand side, we have the dead core, and on the right-hand side, we have the animator core. Most of the hints go through a queue in order to get transferred between these two cores, and the modules that we added to both these cores are highlighted in this figure. So we're going to start with describing the dead core, and we gradually go through the different structures here. The dead core basically runs the same program and provides the hint for the animator core. You can think about it as an external run-ahead engine. It's then 6 issue out of order. And we have instruction cache hints that are basically PC of committed instructions. We have data cache hints that are addresses of committed loads in store, and we have branch prediction hints that are branch prediction updates of the animator core. And one modification that we make here is we make the L1 cache of the animator core to have only read access to the L2 cache, since we want to preserve the memory state. We don't want to write the dirty line back to the shared memory.
So there's something I don't understand about this whole scheme. So I'm designing a processor, and I'm going to have a bunch of cores on it.
Yeah.
So the idea here is that I'm going to put in all this hint gathering logic and ability to drop dirty lines, and then push those out to the small core. Am I doing this from the day I light up the design, or am I only doing it when the first thing fails?
This is for the manufacturing faults. So basically, you will know at the manufacturing time that something is wrong. You need to somehow fix it. Yeah. So I have a slide. I will jump 2 slides ahead. I think that would be useful. That's how we're going to design the system. Oh, go ahead.
If the dead core cannot read what it has written, can it still run ahead far enough to do the deal?
There are different type of failures that are that can happen inside the
It's not allowing it to read what is written because it only has read access to the cache.
No, but it has this local L1 cache, which is L2 is only.
Missing.
Sorry. Okay, so here I have a picture that basically shows how we're going to design this system. This is modeled after Sunrock with 16 cores. Each cluster has 4 cores, and this is how we're gonna. This is how is our vision. Basically, that we share that animator core across several aggressive cores, and at the manufacturing time, we know that whether any of them has a failure or not. Depending on that, we're gonna like hardwire or like burn some fuse or something that's gonna couple one of these with the animator core inside the group. All right, should I move on? So animator core is, as I mentioned, is an older generation running same ISA. Here I assume is a 2 issue out of order, and since it has the precise state, basically we allow it to handle the exceptions. We treat the cache hints to warm up as the prefetching information to warm up the local caches, and we rely on some fuzzy hint disabling approach based on the continuous monitoring of the hint effectiveness to realize that when do we need to disable a particular type of hint to save on the energy and also reduce the contention and the resources of the animator core. And we copy the architectural, the PCN architected registers whenever we realize that the state of the animator, of the dead core is basically so far away from the correct state, and we want to do a resynchronization. Because sometimes it starts executing in the wrong path and goes on, and basically the hints that you're getting at that point is no longer useful. And we do a resync between them. Since most of our communications are unidirectional, we're going to use a single queue for transferring the hints. And L2 warmup is provided free. That means that there is no need for a hardware to do the communication between the two cores.
So there was a lot of work on, slip steaming processors and SSRT and subordinate simultaneous
Yes.
cores and all of this. Is your big advance here? I mean, clearly the coupling for yield is a novel step. Are you adding other hints and mechanisms that do better than the prior work?
Very, very, very good question.
Core acceleration, or are you basically taking the best practices from that prior work and applying it to this topology to
That's
increase
a
yield?
great question. So the biggest advantage that we get in terms of selling point is definitely that we are using it for yield and hard faults. The second thing is that since I would say that the way that we apply it is different from the prior work, but there are some few things that are completely different, and that's mainly this decision to disable a particular type of hints or do the resynchronization, and these are like the fine-grained decisions that we make that are not like the case for the prior work. And basically the way that we design the hint distribution and gathering is based on the fact that we know that we need to disable these hints once in a while.
Yep.
Exactly.
Okay.
So here, for the sake of time, I will skip over cache hints and I'll go over the life cycle of a single branch prediction hints in our system. The thing that's happening is whenever there is a branch prediction update in the dead core, we send a signal to the hint gathering unit and we say that, okay, generate a new hint. It's going to look into the queue. If queue is full, it's going to stall, meaning that the dead core is already too far ahead of the animator core and it does not need to generate any new hints. Otherwise, it's going to get that PC and next PC and add two more fields to it. One is type of the hint and the other one is age tag. Age tag is a field that we use in order to let the animator core know that when to use that particular type of hint, when is the right time to use it. And we inject this hint inside the queue. It gradually goes through the queue and gets to the head of the queue. At the animator core side, we have a buffer that basically buffers these hints and allow basically out of order or random access to the different hints inside of this buffer, because we have like cache hints as well. And whenever the age tag is less than some empirical value, we know that at this point we can use this particular type of hint. And if the hint disabling unit is allowing that hint to be applied locally, we get the hint and we send it to the fetch unit of the animator core. In the fetch unit, we make a small modification. I don't know whether it's small or not. The original predictor of animator core is a simple bimodal. We're going to add another bimodal predictor. We call it Necromancer predictor. And this particular predictor basically will keep track of the hints that are coming. And at the higher level, we apply a tournament predictor that decides for a particular given PC whether the original branch predictor of the animator core should take over or the Necromancer predictor should take over. And we are going to use this tournament predictor to decide whether at a given point in time, whether we should disable the branch prediction hints or not. And this is the slide that describes how we apply Necromancer to a larger CMP system. In summary, we're going to use Necromancer to enhance the throughput of the system by exploiting dead cores, and we leverage a set of microarchitectural techniques to provide intrinsically robust hints, fine and coarse-grained hint disabling, online monitoring of the hint effectiveness, and also dynamic state resynchronization between the two cores. Applying Necromancer to a 4-core CMP, on average, we get 88% of the original performance of a live core, and this comes with a modest area and performance overhead of 5 and 9%.
88% is the performance of the Necromancer core with the hints compared to the original 100 issue core.
Exactly. Compared to the 6 issue core. Exactly.
And it's really just a pair. It's not a 4-core CMP. Yeah.
Yep. It means that it shares it in that manner. That's.
You're talking about a pairing of two cores.
Exactly.
The sharing is not
like sharing for the performance. Exactly. So I guess that I will go over some of the potential future works and some of the concluding remarks if we have time.
So I have one more question.
Okay, go ahead.
So for a 4-core CMP with the Necromancer thing on, let's assume that ignore L2 or anything like that. Yeah. So each core with its L1 and all that is 25% of that cluster. in terms of area.
Yeah.
And now I'm adding a new core plus all of the tracking logic and buffering. And so to add 5.3% area means that the hint plus the new core adds 5.3% area to that, which means that the core is a sixth the size of the other ones, of the big ones?
It's roughly 1/5. This is including the L2s. You see, L2s are already there. So if you remove the L2s, it's going to be a bit more area overhead. You see, including L2, you mentioned that excluding L2s. I'm saying this 5% is including L2s. But the area comparison of the thing that you're interested in is that what's the area of this one compared to this one? Is around the fifth. Yeah.
What are the cache sizes in the two cores?
This one is 64 kilobytes for like data, 64 for instruction, and this one is around 4 kilobytes for each.
Okay.
So it's very, very small.
Yeah, you're
Try to
getting
get it in the smallest.
Yep.
Yep. So I'll go over the future work very quickly. Some of the things that I can basically work on the same area of reliability and low power design is one is the usage of control theory for power management of processor pipeline, caches, and network on chip. That I'm actually currently working on this with some of my, we have some collaboration with Intel Labs, and I have some other students that are working on this at U of I. And another area is we want to exploit process and temperature for reducing the refresh energy of dynamic memories, since dynamic memories are becoming more common on chip. Also, like Power 7 and other processors have it. Basically, usage of temperature and process variation can substantially decrease the number of refreshes that you need to do. Another thing is using more reconfigurable architecture for near threshold voltages, and I have some ideas to extend some of the prior works that I've done for this domain. Another thing is that I'm excited about is to study the newer technology nodes and see that what are the trade-offs between the energy and reliability, for example, for PCM, carbon nanotubes, and spin torque transfer memories. Another thing that I'm excited about is to see if we look at approximate computing, what are the things that basic reliability can contribute to this. For example, some of the things is like understanding the fault propagation and containment, measuring the accuracy of the result, what is an acceptable level of accuracy, limiting the fault rate, devising a fallback mechanism, or even making more applications suitable for this domain. I think these are all interesting challenges in this domain. Here I have a list of publications during the course of my graduate and postgraduate studies. I've worked generally in 3 areas. I worked on reliability and fault tolerance, low power design, and also single thread performance and throughput. In addition to what I've presented, I also worked on some other areas like transient fault recovery, wear-out-centric scheduling, online testing, refresh energy reduction for dynamic memories, energy efficient accelerators, and also application-specific processors. So in conclusion, as you know, we have more transistors these days than what we can power on. Therefore, in order to scale the performance in an energy-constrained environment, we need to improve the computational efficiency. And this needs to rethink the computer architecture for energy efficiency from ground up. As we saw in this talk, reliability and energy efficiency are tradable, and we can take advantage of techniques that can tolerate process variation for this purpose. However, conventional reliability solutions are too expensive for these mainstream high-performance microprocessors. And there is a need for new proposals that can trade reliability and power and energy efficiency by providing runtime adaptability and high degree of reconfigurability. Thank you so much for your time, and I'll be happy to take any further question. I got very, very interesting feedbacks for the first work, and I really appreciate it.
Thank you very much. In the interest of time, I think
You're going to be meeting with most of us anyway.
all right. Questions. Good evening. I have a question. I have to hop out for a call. Thank you for the talk.
All right.
Definitely interactive.
Yeah.
I'll see you at 1:30.
All right. Thanks.
You are on for 1:30?
Yeah.